Hello there and welcome. Tonight we're going to tell the story of a world that has fascinated humanity for thousands of years. Not just any world, but our neighbour in space, Mars. The red planet has been watched, studied and explored more than any other planet besides our own Earth. And what we've learned has completely transformed how we see this rust-coloured dot in the night sky. Before we begin, I want you to get comfortable. This is a journey designed to be experienced at your own pace, whether you're settling in for the evening, winding down after a long day, or simply looking for a calm and contemplative way to explore the cosmos. There's no rush, no urgency, just the steady unfolding of a planetary story that spans billions of years. So adjust your position, take a deep breath, and let yourself relax as we travel together across space and time. This isn't just a collection of facts about Mars. Think of it as a biography, the life story of an entire planet. We'll travel through billions of years, from Mars's violent birth in the early solar system to the cold, quiet world we observe today. We'll explore its mountains and valleys, its vanished rivers and ancient lakes, and we'll ask the question that drives so much of our curiosity. Could Mars have once harboured life? Let the gentle rhythm of this story carry you along. There's something deeply peaceful about contemplating the vast scales of planetary time, the slow dance of geological processes, the patient work of wind and water shaping a world over eons. But before we begin, please take a moment to like and subscribe, but only if you genuinely enjoy what I'm doing here. Also, leave in the comments where you're tuning in from and what time it is there. It's great to see how these videos connect people from around the world. Now settle in, close your eyes if you'd like, and let's embark on this journey across space and time to understand the most explored planet beyond Earth. Every planet has an origin story, and Mars is no exception. About 4.5 billion years ago, our solar system was nothing but a vast cloud of gas and dust, spinning slowly in space. At the centre, our sun was beginning to ignite, while the leftover material started clumping together, building blocks of rock and ice colliding and merging in the chaos of the early solar system. Mars formed in what we call the inner solar system, relatively close to the sun, but farther out than Earth. The rocky material that came together to create Mars was similar to what built Earth, Venus, and Mercury, mostly silicate rocks and metals, like iron and nickel. But Mars had one crucial difference. It formed smaller. Much smaller, in fact. Mars has only about half the diameter of Earth and just over 10% of Earth's mass. Why does size matter? Well, a planet's size determines much of its fate. A smaller planet cools faster. It has weaker gravity, making it harder to hold on to an atmosphere, and it has less internal heat to drive geological activity like volcanoes and plate tectonics. From the very beginning, Mars was dealt a different hand than Earth, and that difference would shape everything that followed. During those early violent days, Mars was bombarded by asteroids and comets, just like all the rocky planets. This period, called the Late Heavy Bombardment, scarred Mars's surface with countless craters, some of which we can still see today. But something else was happening too. Mars was warming up from all those impacts and from the decay of radioactive elements in its interior. The planet became hot enough to melt, and heavier materials like iron sank toward the centre, while lighter rocks floated to the surface. This process, called differentiation, gave Mars its structure: a dense metallic core, a thick rocky mantle, and a thin crust on top. Evidence suggests Mars's core is about half the planet's radius, relatively large compared to its overall size. And here's something interesting. That core appears to be at least partially liquid even today, which we know from how seismic waves travel through the planet, as measured by NASA's InSight lander. But let's pause for a moment and think about what Mars might have looked like back then. The surface would have been glowing red hot from impacts and volcanic activity. There was no oxygen in the atmosphere. Instead, gases like carbon dioxide, water vapor, and nitrogen were being released from the planet's interior through volcanic eruptions. And despite the chaos, something remarkable was beginning to happen. Mars was starting to develop an atmosphere thick enough to support liquid water on its surface, which brings us to one of the most important chapters in Mars's biography, the time when rivers flowed and lakes filled ancient basins on a young, wet Mars. When we look at Mars today, we see a dry, dusty desert world. But the evidence written in the rocks tells a completely different story about the planet's past. For perhaps the first billion years of its history, Mars was a place where water flowed freely across the surface. How do we know this? The answer is written in the landscape itself. When spacecraft orbit Mars and map its surface in exquisite detail, they see something unmistakable: ancient river valleys carved into the rocks. These valleys branch like the veins of a leaf, exactly the way rivers do on Earth. They wind down from highlands into lowland basins, growing wider as they go, gathering tributaries just like the Mississippi River or the Amazon. Some of these valley networks are enormous. Take Valles, for example, a system of channels that stretches for nearly 2,000 kilometers. Scientists think massive floods of water carved these channels, perhaps released catastrophically when underground ice melted or when crater lakes broke through their walls. The scale is hard to imagine, floods that would dwarf anything in Earth's history. But it wasn't just rivers. We've also found clear evidence of ancient lakes, craters that once filled with water, leaving behind layered sediments visible today. Jezero Crater, where NASA's Perseverance rover is currently exploring, is one of these ancient lake beds. You can actually see the delta, a fan-shaped deposit where a river once emptied into the lake, dropping sediment layer by layer. It looks remarkably like river deltas on Earth. Now here's where things get really interesting and a bit controversial. Some scientists think Mars once had an ocean covering much of its northern hemisphere. The evidence? There's a clear boundary between the heavily cratered southern highlands and the smoother northern lowlands, almost like an ancient shoreline. Features that might be ancient beaches have been identified along this boundary, and the northern lowlands are lower in elevation, like an ocean basin. But not everyone is convinced. Other researchers argue that volcanic flows, impacts, or other geological processes could have created these features. The debate continues, and that's actually what makes science exciting. We follow the evidence, we test different ideas, and slowly we get closer to the truth. Whether or not there was an ocean, one thing is certain. Early Mars was much warmer and wetter than it is today. But how was this possible? Mars is farther from the Sun than Earth, so it receives less heat. For liquid water to exist on the surface, Mars would have needed a thick atmosphere, one that could trap enough heat through what we call the greenhouse effect. Scientists think Mars's early atmosphere was dense and rich in carbon dioxide, perhaps with other greenhouse gases like methane. This thick blanket of air kept the planet warm enough for water to remain liquid. Volcanic activity continually replenished the atmosphere, replacing gases that were lost to space or absorbed into rocks. But this brings us to a question that's central to Mars's story. If Mars once had rivers, and possibly even oceans, what happened? Why did it all disappear? The Mars we see today is a pale shadow of its former self. The atmosphere is now incredibly thin, less than 1% the density of Earth's atmosphere. The pressure at Mars's surface is so low that liquid water simply cannot exist there. If you poured a glass of water on Mars today, it would either freeze solid or boil away into vapor almost instantly, depending on the temperature. So what happened to the thick atmosphere that once kept Mars warm and wet? The answer has to do with something Mars lost early in its history: its global magnetic field. Earth has a powerful magnetic field generated by electric currents in its liquid outer core, a natural shield that protects our atmosphere from the solar wind. The solar wind is a stream of charged particles constantly flowing out from the sun, and it's more destructive than you might think. Mars once had a magnetic field too. We know this because ancient rocks in Mars's southern highlands are magnetized. They preserve the memory of that long-lost field. But sometime during the first few 100 million years of Mars's history, the planet's core cooled enough that it stopped generating a global magnetic field. Without this protective shield, Mars became vulnerable. The solar wind began stripping away Mars's atmosphere, particle by particle. Ions in the upper atmosphere were picked up by the solar wind and carried off into space. This process continues today, and we've actually watched it happen. NASA's MAVEN spacecraft, which orbits Mars studying its upper atmosphere, has measured this atmospheric loss in real time. Mars is still losing about 100 tons of atmosphere to space every single day. But the loss of the magnetic field wasn't the only problem. Mars also stopped having widespread volcanic activity. On Earth, volcanoes continually pump gases back into the atmosphere, replacing what's lost. Mars had vigorous volcanism early on, but as the planet cooled, volcanic activity slowed dramatically. Without this replenishment, the atmosphere that was lost to space couldn't be replaced. There's another factor too: Mars's weak gravity. With only about 38% of Earth's surface gravity, Mars simply can't hold on to lighter atmospheric gases as effectively. Over hundreds of millions of years, this made a significant difference. The transformation was gradual, but devastating. As the atmosphere thinned, the greenhouse effect weakened. Temperatures dropped, water began to freeze, rivers dried up or turned to ice, lakes froze, and then slowly evaporated away. By about 3.5 billion years ago, Mars had become the cold, dry desert we recognize today. But not all of Mars's water disappeared into space. Much of it is still there, locked away beneath the surface. The hidden water, ice, frost, and buried reserves. One of the most important discoveries of the past few decades is this: Mars still has a lot of water. It's just not where we might expect to find it. The most obvious place is the polar ice caps. Look at Mars through a telescope, and even from Earth you can see bright white caps at both poles. These aren't just frozen carbon dioxide, dry ice, though there's plenty of that too, especially at the South Pole. Beneath the carbon dioxide ice lies water ice, and lots of it. The North Polar Cap of Mars is primarily water ice, about 1,000 kilometers across and up to 2 kilometers thick in places. If you melted all the water in that ice cap, it would cover the entire surface of Mars in a layer about a meter deep. During Martian winter, carbon dioxide from the atmosphere freezes out at the poles and the ice caps grow larger. In summer, that dry ice sublimes, turns directly from solid to gas, and the caps shrink again. It's a seasonal cycle that's been going on for billions of years, but the polar caps are just the beginning. Orbiting spacecraft carrying ground-penetrating radar have discovered something remarkable. Vast quantities of water ice buried beneath Mars's surface, extending far beyond the polar regions. In the mid-latitudes, regions equivalent to where cities like New York or Paris would be on Earth, there are enormous deposits of nearly pure ice lying just a few meters below the dusty surface. We've even seen this ice directly. When fresh impact craters form on Mars, they sometimes excavate this buried ice, and orbiting cameras catch bright patches of ice visible in the crater walls. Over time, this ice sublimates away as it's exposed to the thin atmosphere. But for a brief window, we can see proof that it's really there. There's water in other forms too. Frost forms on the Martian surface during cold nights, especially near the poles. Seasonal frost deposits of carbon dioxide ice create intricate patterns across the landscape. And scientists think there might be briny liquid water, extremely salty water that can stay liquid even at very cold temperatures. flowing briefly on steep slopes during warm seasons, though this remains an active area of research. Perhaps most intriguingly, radar measurements suggest there might be liquid water trapped deep underground. In 2018, scientists announced the detection of what appears to be a lake of liquid water beneath the South Polar ice cap, about 1.5 miles below the surface. The water would need to be extremely salty, a concentrated brine, to stay liquid at such cold temperatures. Other similar reflections have been detected, though the interpretation of this data is still being debated. Why does all this water matter? For one thing, it tells us Mars's water didn't vanish completely. It just changed location and form. But more importantly, if humans ever establish a presence on Mars, water will be essential. We need it for drinking, for growing food, for producing oxygen and rocket fuel. Knowing where Mars's water reserves are located and how to access them is crucial for any future exploration plans. But let's step back from the subsurface for a moment and look at what dominates Mars's landscape. Its spectacular geological features. Mountains of giants, the geology of Mars. If you could stand on Mars and look around, you'd see landscapes that would take your breath away. Mars is a geologist's paradise, with some of the most extreme features in the entire solar system. Let's start with the most famous, Olympus Mons. This is not just a mountain, it's the largest volcano in the solar system. Olympus Mons rises about 22 kilometers above the surrounding plains, which is 2.5 times the height of Mount Everest. But what's even more impressive is its sheer size. The volcano is roughly 600 kilometers across, about the size of the entire state of Arizona. If you stood at the base of Olympus Mons and looked up, you wouldn't even be able to see the top. It would be beyond the horizon. How did such a massive volcano form? On Earth, our tectonic plates are constantly moving, so volcanic hotspots create chains of islands like Hawaii. But Mars doesn't have plate tectonics, at least not anymore. A volcanic hotspot stayed in one place for millions of years, continuously building up the same volcano higher and higher. The low gravity also helped. Structures can be taller on Mars because there's less gravitational pull trying to collapse them. Olympus Mons isn't alone. It's part of a region called Tharsis, a massive volcanic plateau roughly the size of North America. Tharsis hosts 4 giant shield volcanoes, including Ascraeus Mons, Pavonis Mons, and Arsia Mons, each of which would be impressive by Earth standards. This enormous pile of volcanic rock actually warped Mars's entire shape, creating a bulge on one side of the planet. But Mars isn't just about volcanoes. On the opposite side of the planet from Tharsis lies something equally dramatic. Valles Marineris, the largest canyon system in the solar system. If you placed Valles Marineris on Earth, it would stretch from New York to Los Angeles, about 4,000 kilometers long. In places, it's 7 kilometers deep and 200 kilometers wide. By comparison, Earth's Grand Canyon is tiny, only about 800 kilometers long and just over a kilometer deep. How did Valles Marineris form? Scientists think the growth of the Tharsis bulge played a role. As that massive volcanic region pushed upward, it may have created enormous stresses in Mars's crust, causing it to crack and collapse. Other processes, landslides, erosion, and perhaps even water flow, then widened and deepened the canyons over billions of years. What's remarkable is that while Earth's surface is constantly being recycled through plate tectonics, erasing ancient features, Mars has preserved its geological history. Craters billions of years old are still visible. Ancient volcanic flows remain largely unchanged. In a sense, Mars is a museum of its own past, allowing us to read the story written in its rocks. The different regions of Mars also tell us about different eras in the planet's history. Scientists have divided Martian history into 3 main periods: the Noachian, the Hesperian, and the Amazonian. These names come from specific regions on Mars and represent progressively more recent periods. The Noachian period, spanning from Mars's formation to about 3.7 billion years ago, was the era of heavy bombardment and possibly widespread water. The heavily cratered southern highlands date from this time. The Hesperian period, from about 3.7 to 3.0 billion years ago, saw volcanic activity and catastrophic flooding, but conditions were beginning to dry out. The Amazonian period extends from about 3 billion years ago to the present, the long cold dry era that characterizes modern Mars. But here's something to consider. Even though Mars has been cold and dry for billions of years, it hasn't been completely geologically dead. Evidence suggests some volcanic activity continued relatively recently. Young lava flows on Mars might be only a few 100 million years old, ancient by human standards, but young in geological time. There may have even been volcanic eruptions in the last few million years, which raises an interesting question. Could Mars still have active volcanism today? We haven't seen direct evidence of current eruptions, but we can't rule it out completely. And that possibility adds another layer of interest to the planet's ongoing story. The Martian atmosphere and weather, dust storms and seasons. Despite being incredibly thin, Mars's atmosphere is far from boring. In fact, it drives weather patterns and seasonal changes that reshape the planet's appearance throughout the year. The Martian atmosphere is about 95% carbon dioxide, with small amounts of nitrogen, argon, and traces of oxygen, water vapor, and other gases. The atmospheric pressure at the surface is only about 600 pascals on average, less than 1% of Earth's sea level pressure. If you stood on Mars without a spacesuit, your blood would literally boil due to the low pressure, even if you could somehow survive the cold and lack of oxygen. But even this thin atmosphere creates weather. Mars has clouds, though they're generally thin and wispy. Some are made of water ice, similar to cirrus clouds on Earth. Others, particularly at high altitudes, are composed of carbon dioxide ice. During cold mornings in some regions, fog can form in valleys, just like on Earth. The most dramatic Martian weather phenomenon, however, is dust storms. Mars is a dusty planet. The iron oxide dust that gives the planet its rusty red colour covers much of the surface. When winds pick up this fine dust, it can stay suspended in the thin atmosphere for long periods. Small dust storms are common and occur regularly, but every few years something more spectacular happens. A dust storm grows and spreads until it eventually encircles the entire planet. These global dust storms can last for weeks, or even months, completely obscuring the surface from view. The dust absorbs sunlight and warms the atmosphere, which creates even stronger winds, which pick up more dust, a feedback loop that sustains the storm. In 2018, a global dust storm essentially ended NASA's Opportunity rover's mission. The rover, which had been exploring Mars for nearly 15 years, relied on solar panels for power. When dust blocked out the sun, Opportunity couldn't generate electricity. The rover went into a low-power hibernation mode and never woke up again, a poignant reminder that Mars is an unforgiving environment. Mars also experiences seasons, much like Earth. Why? Because Mars's rotation axis is tilted at about 25 degrees relative to its orbital plane around the Sun, remarkably similar to Earth's 23.5-degree tilt. This tilt means different hemispheres receive more direct sunlight at different times of year. A Martian year lasts 687 Earth days, so each season is roughly twice as long as on Earth. During northern spring and summer, the North Polar ice cap shrinks as carbon dioxide and some water ice sublimate. During southern winter, carbon dioxide freezes out at the South Pole, and that cap grows larger. The seasonal cycle of carbon dioxide freezing and sublimating actually changes the planet's atmospheric pressure by about 25% over the course of a year. Temperature variations on Mars are extreme. At the equator during summer, afternoon temperatures can reach a relatively pleasant 20 degrees Celsius, about room temperature. But at night, temperatures plummet to around -70 degrees Celsius. At the poles during winter, it gets even colder, down to -125 degrees Celsius, cold enough that carbon dioxide freezes out of the atmosphere. What about wind? With such a thin atmosphere, you might think Martian winds wouldn't be very strong. And in terms of force, you'd be right. Even strong winds on Mars would feel like a gentle breeze on Earth because there's so little air. But Martian winds can reach high speeds, up to 100 kilometers per hour or more during storms, and they're quite effective at moving the fine dust. These winds create some beautiful features. Sand dunes on Mars form just like dunes on Earth, shaped by the prevailing winds. Some areas have fields of dark sand dunes that shift and migrate over time. Wind also creates features called dust devils, small whirlwinds that leave dark tracks across the dusty surface as they sweep away the brighter dust layer and reveal darker material beneath. Living on Mars would mean dealing with this environment every day: the cold, the low pressure, the dust that gets into everything, the radiation from space with no thick atmosphere or magnetic field to shield you. But it's these very challenges that make Mars such a compelling place to study. It's different enough to teach us about planetary processes, yet similar enough to Earth that we can understand it. The moons of Mars, Phobos and Deimos. Mars doesn't orbit the Sun alone. It has two small companions, two moons called Phobos and Deimos. These tiny, irregularly shaped worlds are quite different from Earth's large round moon, and their story adds another intriguing chapter to Mars's biography. Phobos is the larger of the two, measuring about 22 kilometers across at its widest point. Deimos is even smaller, just 12 kilometers across. Neither moon is spherical. They're lumpy, potato-shaped objects, pockmarked with craters. When you see detailed images of Phobos, it looks almost like a giant asteroid, which is essentially what many scientists think it might be. Where did these moons come from? That's actually a puzzle that scientists are still working to solve. One possibility is that they're captured asteroids, rocky bodies from the asteroid belt that Mars's gravity pulled into orbit billions of years ago. Both moons are composed of material that seems similar to certain types of carbon-rich asteroids, which supports this idea. But there's a problem with the capture hypothesis. Captured moons typically have elliptical, tilted orbits, yet both Phobos and Deimos orbit Mars almost perfectly above the planet's equator, in nearly circular paths. That suggests they formed from a disk of material around Mars, similar to how we think Earth's moon formed from debris after a giant impact. Perhaps Mars was struck by a large object early in its history, and the debris from that collision eventually coalesced into Phobos and Deimos. Or maybe they formed from material that was already in orbit around Mars during the planet's formation. The truth is, we're not entirely certain, and this remains an active area of research. What makes Phobos particularly interesting is its orbit. It circles Mars extremely quickly, completing one orbit in just 7 hours and 39 minutes. That's faster than Mars itself rotates, which takes about 24 hours and 37 minutes. This means if you were standing on Mars watching Phobos, you'd see it rise in the west and set in the east, the opposite of how we see the moon from Earth. And you'd see it cross the sky 2 or 3 times in a single Martian day. But here's something remarkable. Phobos is gradually spiraling inward toward Mars. Tidal forces are slowing its orbit, causing it to drop closer to the planet by about 2 centimeters per year. Eventually, in about 50 million years, Phobos will either crash into Mars's surface or break apart into a ring of debris around the planet. Either way, Mars won't have this moon forever. Deimos, being farther out, is in a more stable orbit. It orbits Mars once every 30 hours, which is only slightly longer than a Martian day. From Mars's surface, Deimos would look like a very bright star rather than a substantial moon. It's simply too small and too distant to appear as anything more. Both moons are heavily cratered, showing their age and the battering they've received from impacts over billions of years. Phobos has one particularly prominent crater called Stickney, about 9 kilometers across, so large relative to the moon's size that the impact which created it probably came close to shattering Phobos entirely. Despite their small size, Phobos and Deimos have been targets of scientific interest. Several missions have photographed them in detail, and there have been proposals to send spacecraft to land on them and return samples to Earth. Studying these moons could tell us more about the early solar system and might even provide useful resources for future human missions to Mars. Phobos, in particular, might serve as a staging ground or base for Mars exploration, a place to establish infrastructure before descending to the planet's surface. So while Phobos and Deimos might seem like minor characters in Mars's story, they're actually fascinating worlds in their own right, with their own mysteries to solve and their own roles to play in the future of Mars exploration. The great question: life on Mars? Of all the questions we can ask about Mars, one stands above all others. Has Mars ever harboured life? This isn't idle speculation. Mars once had conditions that, as far as we understand them, could have supported life. Liquid water flowed on the surface. There was a thicker atmosphere. Chemical elements necessary for life as we know it: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur were all present. On Earth, wherever we find liquid water and energy, we find life. So it's reasonable to wonder whether the same might have been true on Mars. Let's be clear about what we're talking about. No one is suggesting that complex animals or plants ever lived on Mars. The question is whether Mars might have hosted microbial life, simple, single-celled organisms similar to bacteria, and whether, if such life did exist, any trace of it might remain today, either as fossils or perhaps even as dormant or active microbes in protected environments beneath the surface. The search for life on Mars has driven much of our exploration. In the 1970s, NASA's Viking landers carried experiments specifically designed to detect signs of life. The results were ambiguous and controversial. One experiment seemed to show positive signs, but the interpretation is still debated today. Most scientists think the Viking results can be explained by chemical reactions in the Martian soil rather than by biology, but we can't be completely certain. Since Viking, our strategy has shifted. Instead of directly searching for life, we've focused on understanding Mars's habitability, whether conditions suitable for life ever existed. And the answer to that question is a clear yes. Multiple Mars rovers have found evidence that ancient Mars had environments that could have supported life. NASA's Curiosity rover, exploring Gale Crater, discovered mudstone, rock formed from ancient mud deposited in a lake. Chemical analysis showed that this ancient lake had fresh water, not too acidic or too alkaline, with the right chemical ingredients for life. We found evidence of organic molecules, complex carbon compounds, in Martian rocks. Now, organic molecules aren't necessarily biological. They can form through non-biological processes too, but they're the building blocks life would need. The current Perseverance rover is taking the search a step further. It's exploring Jezero Crater, that ancient lake bed with a river delta, specifically looking for signs of past life. Perseverance is equipped with instruments that can examine rocks at a microscopic level, looking for textures and patterns that might be biosignatures, signs that life once existed there. The rover is also collecting and caching rock samples that a future mission might return to Earth, where we could study them with laboratory instruments far more sophisticated than what we can send to Mars. But what about life on Mars today? The surface is harsh, cold, dry, bathed in ultraviolet radiation that would quickly destroy any organic molecules. But beneath the surface might be a different story. We know there's water ice underground, and possibly even liquid water in deep brines. Could microbes survive in such environments, perhaps in a dormant state, waiting for conditions to improve? On Earth, we found microbes in extreme environments, in Antarctic ice, in hot springs, in rocks deep underground. Life is remarkably tenacious. It's not impossible that Martian microbes, if they ever existed, found refuges where they could persist. There's another possibility too. Perhaps life never originated on Mars at all, but Earth and Mars exchanged material. We know that impacts can blast rocks off the surface of a planet and send them into space. Some of these rocks can travel between planets. Martian meteorites have been found on Earth. We have pieces of Mars in our laboratories. The transfer could go the other way too. Could Earth life have hitchhiked to Mars on a rock billions of years ago? Or could Martian life have seeded Earth? These ideas sound like science fiction, but they're taken seriously. The concept is called panspermia, and while it's speculative, it's based on real possibilities. The question of life on Mars matters for profound reasons. If we find that life arose independently on Mars, it would tell us that life is common in the universe, that wherever conditions are right, life tends to appear. That would be one of the most significant discoveries in human history. On the other hand, if we thoroughly search Mars and find no trace of life, that's also important information. It might tell us that life is rare, or that the conditions needed are more specific than we thought. We don't have the answer yet. But we're methodically gathering the evidence we need to answer this question, possibly within our lifetimes. Exploring the Red Planet. Missions to Mars. Our understanding of Mars hasn't come from telescopes alone. It's come from a sustained effort to send robotic explorers to the planet, orbiters, landers, and rovers that have gradually pieced together Mars's story. The first successful mission to Mars was NASA's Mariner 4, which flew past the planet in 1965, returning 22 grainy black and white images. Those first pictures revealed a cratered, moon-like surface and shattered expectations that Mars might be an Earth-like paradise. But they also marked the beginning of an era of exploration that continues today. In the decades since, dozens of missions have been launched toward Mars by space agencies around the world. NASA, the European Space Agency, Russia, India, the United Arab Emirates, and China. Not all have succeeded. Mars has a reputation for being a difficult target, but the successful missions have revolutionized our understanding. The Viking missions of the 1970s were the first to successfully land on Mars and conduct science experiments. They sent back the first colour images from the surface, showing a rocky, rust-coloured landscape beneath a pink sky. They studied Martian soil chemistry and even conducted those controversial life detection experiments we mentioned earlier. The 1990s brought a new generation of missions. Mars Pathfinder landed in 1997, deploying a small rover called Sojourner, about the size of a microwave oven. Sojourner was the first rover to explore Mars, though it didn't travel far, just about 100 meters over nearly 3 months. But it proved that rovers could work on Mars, setting the stage for more ambitious missions. In 2004, NASA landed twin rovers, Spirit and Opportunity, designed to last 90 days. Instead, Spirit operated for 6 years, and Opportunity for nearly 15 years, travelling a total of 45 kilometres across the Martian surface. These rovers found definitive evidence that liquid water once existed on Mars. They analysed rocks that had clearly formed in water, found minerals that only form in the presence of water, and discovered what appeared to be ancient lake beds. Meanwhile, orbiters continued mapping Mars from above. Mars Global Surveyor, Mars Odyssey, Mars Reconnaissance Orbiter, and others have created detailed maps of the entire planet, studied its atmosphere, searched for water ice, and served as communication relays for surface missions. In 2012, NASA landed the car-sized Curiosity rover in Gale Crater. Curiosity is a mobile laboratory equipped with a drill to collect rock samples and a suite of instruments to analyze them. It's been climbing Mount Sharp, a mountain of layered sediments in the center of the crater, reading the geological history preserved in those layers, like pages in a book. The latest rover, Perseverance, landed in February 2021. Along with searching for signs of ancient life, Perseverance is testing technologies for future human missions. It carries an instrument called MOXIE that converts carbon dioxide from the Martian atmosphere into oxygen, demonstrating technology that future astronauts might use to produce breathable air and rocket fuel. Perseverance also brought along a small helicopter called Ingenuity, which became the first aircraft to fly on another planet, demonstrating that powered flight is possible in Mars's thin atmosphere. Other nations have achieved remarkable milestones too. The European Space Agency's Mars Express has been orbiting since 2003, and its lander, Beagle 2, reached the surface, though it failed to fully deploy. India's Mars Orbiter mission, also known as Mangalyaan, successfully entered orbit on its first attempt in 2014, an impressive achievement. The United Arab Emirates Hope Orbiter arrived in 2021, studying Mars's atmosphere and climate. And China successfully landed its Zhurong rover in 2021, making China only the second country to operate a rover on Mars. Each mission builds on previous ones, answering old questions and raising new ones. We now have high-resolution maps showing every region of Mars. We've studied its geology, chemistry, atmosphere, and climate. We've confirmed the presence of water ice and possible liquid brines. We've characterized the radiation environment and tested technologies for future missions. But there's still so much we don't know, and that's why exploration continues. The future, humans on Mars. For decades, Mars has represented not just a subject of scientific study, but a destination, a place where humans might one day walk. The question is no longer whether it's possible to send humans to Mars, but when we'll actually do it, and how. Getting to Mars is no simple matter. The planet is, on average, about 225 million kilometers from Earth, though this distance varies significantly depending on where both planets are in their orbits. At their closest approach, which occurs roughly every 26 months, Mars is only about 55 million kilometers away. These close approaches, called launch windows, are when it makes sense to send missions to Mars, and they last for only a few weeks. A one-way trip to Mars with current propulsion technology takes about 6 to 9 months. That means astronauts would spend half a year in a spacecraft exposed to cosmic radiation and microgravity before even arriving. Once there, they'd need to stay for at least a year and a half before Earth and Mars align favourably again for a return trip. So a round-trip mission to Mars would take at least 2.5 to 3 years, a commitment far beyond anything we've done before. The challenges are formidable. Astronauts would need life support systems that can recycle air and water for years. They'd need reliable power, solar panels, and possibly nuclear reactors. They'd need to grow or produce at least some of their own food. They'd need radiation shielding to protect against cosmic rays and solar storms. They'd need habitats that can keep them safe from the harsh Martian environment. And perhaps most challenging, they'd need to deal with the psychological effects of isolation, confinement, and living millions of kilometers from Earth, with no possibility of quick rescue if something goes wrong. But despite these challenges, serious planning is underway. NASA's current vision involves establishing a gateway station in lunar orbit, testing technologies on the Moon, and then applying those lessons to Mars missions, possibly sending humans to the Red Planet in the 2030s or 2040s. Private companies, particularly SpaceX, have announced even more ambitious timelines, though these are likely optimistic. What would a Mars mission actually look like? Current concepts involve sending cargo missions first, unmanned spacecraft that would deliver supplies, equipment, and a return vehicle to Mars before humans even leave Earth. This reduces risk and ensures that everything astronauts need is already waiting for them. The first human mission might land near the equator in the Martian surface. A closer look at the rocks beneath our rovers. While we've discussed Mars's grand features, its towering volcanoes and vast canyons, there's another side to understanding this planet that requires us to look much closer. The rocks themselves, the dust that covers nearly everything, and the soil that rovers have scooped up and analysed tell us stories that we couldn't learn any other way. When you look at images from the Martian surface, one of the first things you notice is the colour. That distinctive rusty red isn't just a trick of the light, it's iron oxide, essentially rust. Mars is red because its surface rocks contain iron that has been oxidized or rusted over billions of years. But how did this happen on a planet that has very little oxygen in its atmosphere today? The answer likely goes back to when Mars had a thicker atmosphere with more water vapour. Chemical reactions between water, rocks, and whatever oxygen was present slowly oxidized the iron in Martian rocks. Once this process started, it continued even as Mars dried out, because ultraviolet radiation from the sun can also drive oxidation reactions in the thin atmosphere we see today. But not all of Mars is red. If you look at high-resolution images from orbit, you'll see that Mars is actually quite colourful in places. There are regions of dark grey basalt, volcanic rock, similar to what forms Hawaii's black sand beaches. There are lighter coloured areas where sulfate minerals have accumulated, and there are the polar regions, which shift between white and brown as ice accumulates and sublimates with the seasons. The dust itself is fascinating. Martian dust is incredibly fine. Particles are typically only a few micrometers across, about the width of a bacterium. This is much finer than most dust on Earth, and it's one reason why Martian dust storms can loft particles so high into the atmosphere and keep them suspended for so long. This fine dust is also a problem for solar-powered spacecraft because it settles on solar panels and reduces their efficiency. But here's something interesting. Martian dust devils and winds sometimes clean dust off solar panels. The Spirit and Opportunity rovers both experienced unexpected cleaning events where their power output suddenly increased because wind had swept away accumulated dust. It's a reminder that Mars, while harsh, occasionally offers helping hands to our robotic explorers. The composition of Martian soil has surprised scientists. Chemical analyses by rovers have found that Martian soil is more complex than expected. It contains perchlorates, salts that are highly oxidizing and somewhat toxic to life as we know it. This was unexpected, and it complicates the search for life because perchlorates can destroy organic molecules. But interestingly, perchlorates also lower the freezing point of water, which means they could allow briny liquid water to exist at temperatures where pure water would freeze solid. Different regions of Mars have different rock types, revealing different chapters in the planet's geological history. In some areas, rovers have found conglomerate rocks, stones that clearly formed in flowing water, with rounded pebbles cemented together, just like river rocks on Earth. In other regions, there are finely layered sedimentary rocks that settled out slowly in calm water, probably at the bottom of ancient lakes. We've also found volcanic rocks, of course. Some areas show basaltic lava flows that look remarkably similar to lava flows in Iceland or Hawaii. Chemical analysis reveals that Martian basalts have slightly different compositions from Earth's basalts, telling us about differences in the planet's interiors and the processes that generate magma. One of the most intriguing discoveries has been what scientists call blueberries, small round concretions of hematite, another iron oxide mineral found by the Opportunity rover. These millimetre-sized spheres formed in the presence of water, likely when groundwater-carrying dissolved minerals percolated through rocks and precipitated out, forming these small hard nodules. Similar features form on Earth in wet environments, and finding them on Mars was strong evidence for ancient water. The rocks also preserve evidence of Mars's ancient magnetic field. Certain minerals in rocks can lock in the direction of magnetic fields as they form, like tiny frozen compasses. By studying magnetized rocks, especially in Mars's southern highlands, scientists have determined that Mars once had a magnetic field that was probably comparable in strength to Earth's field today. The pattern of magnetization suggests the field shut down relatively early in Mars's history, probably within the first few 100 million years. Understanding Martian geology isn't just academic, it has practical implications for future exploration. If humans are going to live on Mars, they'll need to use local materials for construction. Could Martian rocks be melted down and 3D printed into habitats? Could minerals be extracted and processed into useful materials? These are questions engineers are actively considering. There's also the matter of landing sites. Every Mars mission requires careful selection of landing sites, flat enough to be safe, interesting enough scientifically, and accessible enough that rovers can explore interesting terrain. Scientists spend years studying potential landing sites from orbit, mapping rocks and slopes before committing to a location. One thing that strikes many people when they see images from Mars is how familiar it looks in some ways. Yes, the sky's pinkish instead of blue. And yes, there are no plants or animals. But the rocks, the hills, the layered cliffs, they look like places you might find in the American Southwest or other desert regions on Earth. It's both alien and familiar at the same time, which is part of what makes Mars so compelling. The more we study Martian rocks and soil, the more we realize how much information they contain. Every pebble, every grain of sand, every exposed cliff face is a page in the history book of Mars. And we're learning to read that book more fluently with each passing mission. The rocks tell us where water flowed, where volcanoes erupted, how the climate changed, and what chemical processes shaped the surface. They might even eventually tell us whether life ever arose on the red planet. In many ways, the story of Mars is written in its rocks, and we've only just begun to read it. Mars in human culture, from ancient mythology to modern science. Before we conclude our journey through Mars's scientific biography, it's worth stepping back to consider how this planet has captured human imagination throughout history. Mars's influence on human culture stretches back thousands of years, long before we had any idea what it actually was. Ancient civilizations noticed Mars because of its colour and its behaviour in the sky. Unlike stars, which maintain fixed positions relative to each other, Mars wanders across the sky against the background of stars. That's why it was called a wandering star or planet, from the Greek word planetes, meaning wanderer, and that distinctive blood-red colour made it stand out. The ancient Babylonians associated Mars with their god of war and destruction, Nergal. The Greeks called it Ares, after their god of war. When the Romans adopted Greek astronomy and mythology, they kept the war association, but renamed the planet Mars after their own war god. That's the name that stuck. Why associate Mars with war? Probably because of its colour, the red of blood and fire. Ancient peoples, seeing this red wanderer in the night sky, imagined it represented conflict and destruction. Interestingly, cultures around the world independently made similar associations. In Hindu astronomy, Mars is called Mangala, associated with conflict and warfare. In Chinese astronomy, Mars is Huoxing, the fire star, associated with heat and chaos. Fast forward to the late 1800s, and Mars became the centre of perhaps the most famous mistaken belief in astronomical history. Italian astronomer Giovanni Schiaparelli, observing Mars through telescopes, reported seeing what he called canali, channels. In Italian, this word simply means channels, natural features, but when translated into English, it became canals, implying artificial construction. This sparked an obsession, particularly in American astronomer Percival Lowell, who became convinced that Mars was inhabited by an advanced civilization that had built a planet-wide system of canals to transport water from the polar ice caps to the dry equatorial regions. Lowell wrote extensively about Martian civilization, mapping hundreds of canals and speculating about the dying Martian race struggling to save their desiccating planet. It was compelling fiction, but it was fiction nonetheless. The canals were optical illusions, artifacts of the human brain's tendency to see patterns where none exist, combined with the limitations of telescopes at the time. When better telescopes and later spacecraft revealed Mars as it actually is, the canals vanished. They had never been there, but the idea of Martian civilizations had already captured popular imagination. H.G. Wells wrote The War of the Worlds in 1898, imagining hostile Martians invading Earth. Edgar Rice Burroughs created John Carter, who travelled to Mars, called Barsoom in his novels, and had adventures with various Martian cultures. These stories and countless others established Mars as the home of aliens in popular culture, a role it maintained throughout the 20th century. The irony is that while we now know Mars has no cities or civilizations, the planet has turned out to be far more interesting than Lowell's canals. Ancient rivers, extinct volcanoes, larger than any on Earth, evidence of past habitability. The real Mars is remarkable enough without needing to invent intelligent Martians. Today, Mars represents something different in human culture. It's not the home of gods of war or dying alien civilizations. It's a destination, the next place humans might expand beyond Earth. Mars has become a symbol of exploration, of the future, of human potential and ambition. This shift reflects our growing understanding that Mars, while challenging, is potentially within our reach. It's close enough that we can actually imagine going there, different enough to be exciting, but similar enough to Earth that survival seems possible with the right technology. Mars continues to inspire art, literature, and film. From The Martian, which portrayed scientifically grounded survival on Mars, to discussions of Mars colonies in science and policy forums, the planet looms large in our collective vision of humanity's future. Whether that future actually includes Martian settlements remains to be seen, but the cultural impact is undeniable. In a sense, we've come full circle. Ancient peoples looked at Mars and saw a god. For centuries we looked at it and wondered what it might be. Then we looked closer and saw it for what it actually is, a cold, dusty desert world with a complex past. And now, looking forward, we see it as something else again, a challenge, an opportunity, perhaps even a future home. Mars has always been more than just a planet to us. It's been a mirror for our fears, our hopes and our imagination. And as we continue to explore it, that relationship deepens and evolves. Flat area, possibly where we've already identified ice beneath the surface. The crew would set up habitats, deploy power systems, and begin producing oxygen and water from local resources, a concept called in situ resource utilization, or ISRU. Instead of bringing everything from Earth, astronauts would make what they need from Martian materials. One of the most crucial ISRU technologies is producing rocket fuel on Mars. The Martian atmosphere is mostly carbon dioxide, and there's water in the form of ice. Using energy from solar panels or nuclear reactors, astronauts could split water into hydrogen and oxygen and combine the hydrogen with carbon dioxide to make methane fuel. This would dramatically reduce the mass that needs to be launched from Earth, making Mars missions more feasible. What would astronauts actually do on Mars? Science certainly. Exploring regions where rovers can't easily go, collecting samples, conducting experiments, but longer-term visions include establishing a permanent presence, a research station that grows over time, perhaps even evolving into something approaching a settlement. Could Mars be terraformed, transformed into a more Earth-like world? This is a much longer-term and more speculative idea. In theory, if we could release carbon dioxide and water vapour trapped in Mars's ice caps and rocks, we might thicken the atmosphere enough to raise temperatures and allow liquid water on the surface again. But this would require technologies and resources far beyond what we currently have, and the ethical questions are complex. Do we have the right to deliberately alter an entire planet? What if Martian life exists somewhere beneath the surface? For now, these are questions for the distant future. The near-term goal is simply to get humans to Mars and return them safely, to prove it can be done. If that succeeds, everything else becomes possible. Mars and Earth, planetary siblings. Throughout this journey through Mars's biography, you might have noticed something. Mars and Earth have a lot in common. They're both rocky planets in the inner solar system. They both have tilted axes and experience seasons. They both have ice caps. They both have weather, wind, clouds, storms. Days on Mars are only about 40 minutes longer than Earth days. In many ways, Mars is Earth's sibling, but they're siblings who took very different paths in life. Earth kept its thick atmosphere and strong magnetic field. Plate tectonics continually renew our planet's surface, recycling materials and driving geological activity. Our oceans cover most of the surface, moderating temperatures and hosting an abundance of life. Earth is, as far as we know, the only world in the universe where life has definitively taken hold and flourished. Mars lost its magnetic field early. Its atmosphere thinned. Its water froze or was lost. Geological activity slowed and eventually nearly stopped. The planet that might once have been a warm, wet world became a cold, dry desert, possibly sterile. Why did these two planets diverge so dramatically? Size appears to be a crucial factor. Earth is larger, with stronger gravity, more mass and more internal heat. That allowed our planet to maintain the geological processes that keep it dynamic and alive. Mars, being smaller, cooled faster and couldn't maintain those processes. But studying Mars isn't just about understanding Mars, it's about understanding Earth too. By comparing these two worlds, we learn what makes a planet habitable. We learn what processes are essential for maintaining a life-friendly environment. And we gain perspective on how fortunate Earth has been. Mars also serves as a reminder that planetary environments aren't static. Earth has been habitable for billions of years, but that's not guaranteed to continue forever. Our sun gradually brightens as it ages, and in a billion years or so, Earth's oceans might evaporate. On much shorter timescales, humans are currently changing Earth's climate in ways that could make parts of our planet less hospitable. Understanding planetary climate systems, both on Earth and on Mars, helps us recognize what's at stake. In a sense, Mars is a cautionary tale. It shows us that even a planet that starts with favorable conditions can lose its habitability. But it's also a story of resilience. Despite being cold, dry, and apparently lifeless for billions of years, Mars still holds interest, still holds secrets, and might still harbour surprises. The ongoing story. We've travelled billions of years through Mars's story, from its violent birth to the cold, quiet world we see today. We've explored its mountains and valleys, its vanished rivers, and hidden ice reserves. We've asked whether life might once have existed there, or might even exist today in some deep refuge. We've followed the spacecraft and rovers that have gradually revealed Mars's secrets. and we've looked ahead to a future where humans might walk on its surface. But here's the remarkable thing: Mars's story isn't finished. It's an ongoing narrative that we're actively writing through exploration and discovery. Every new mission reveals something unexpected. Every analysis of Martian rocks raises new questions. Every technological advance brings human missions closer to reality. What will we learn about Mars in the next decade? Will perseverance find clear evidence of ancient life in those lake sediments? Will future missions detect present-day life beneath the surface? Will we discover resources that make long-term human presence more feasible? Will the first human footprints appear in Martian dust in our lifetimes? We don't know yet, and that's part of what makes this story so compelling. Mars is close enough that we can study it in detail, different enough to teach us about planetary processes and possibilities, and familiar enough that we can imagine living there. It's a world that bridges the familiar and the alien, the past and the future. For thousands of years, humans have looked up at that red dot in the night sky and wondered. For centuries, we've studied it through telescopes, imagining what it might be like. For decades, we've sent robotic explorers to see it up close. And perhaps soon, human eyes will gaze directly upon Martian landscapes, and human minds will ponder the questions we've raised today while standing on Martian soil. Mars's biography is one of transformation, from a warm, wet world to a cold desert. But it's also a story of persistence. After billions of years, Mars endures, still fascinating us, still holding secrets, still beckoning us to explore. Thank you for joining me on this journey through the life story of Mars. Every time you see that reddish point of light in the night sky, remember, you're looking at a world with a deep history, an active present, and possibly a future that includes us. The Red Planet story continues, and in some small way, we're all part of it now. Clear skies, and keep looking up.